direction. This is why it's 1. If they were in different direction, then we were having 0. The nuclear magnetic moment of the deuterium is 0.86, and the sum for the free proton is 0.88. Okay, after this study, then the scientists begin to thinking, okay, now we can also see how much is going to be the potential, how is the nuclear potential inside the nucleus. Then if you bombing neutrons and protons, then you can find out how is the behavior of the different, the neutron and the proton. Then we had that it's going to have some minimum value. Yeah, and then after that is going to be close to 0. Or if we had proton with proton, then we're going to have minimum value, but in some point it's going to increase a little, and then after that it's going to go down again. Okay, then with this, then we can begin to understand how is the nuclear form. We can see where are the stability, the stable points, and the difference between the different values at the stability and separation. The nuclear force is known to be spin dependent, as we say, because you know we had the proton and the neutron, then depend a lot of the spin that we had. The neutron and proton spin and align, and we said before, and it's gonna bond the state of neutron, but there is no bond state for the spin anti-alignment. Yeah? Then in this case we are not gonna have. NN system is more difficult to study because free neutrons are not stable for analysis experiment. This means if we had a system only with neutron is not stable, then it's gonna be moving and it's not gonna be enough to have analysis of the experimental data. Another important thing is that the nuclear potential between two nucleons seem independent of their charge. This means the charge is independent of the nuclear force. Then in this case we are not going to have. And the term nucleon refers either to neutron or proton because the neutron and proton can be considered different charge states relating to exactly the same particle. Then we are going to have the total value. Now, an interesting thing that we can see is how is the nuclear stability in terms of the bonding. I would like you to look this graphic here and try to tell me is what you think when you see this kind of graphic. Here we have the proton number, and here we have the neutrons number. Here is going to be the line of stability, and these data are shown the experiment using the different elements and trying to understand the stability. Now, my question is, if you look this graphic here, for example, you do an experiment, and then you find this result, and this is your line of stability. What can you conclude, or what can you say about this thing? You can say something, or? I didn't get into the question.
What does it mean to be above or below the line?
Well, the line is just a one-to-one
This line.
of neutrons and
This one is the
protons.
one that is showing like the, for example, if you had equal neutrons and equal, you see, neutron number n and then proton number. If they were equal, this is the line of stability. But then, if you had other elements like other chemicals, then you're going to find other results. The point is what this means. Then, for example, I'd like you to look this number here. Proton number 40 here. If you look before, you can see that this curve kind of had some overlap. You see? Two lines kind of share something. Then you can say, okay, here, after this point, you see that these are going up, but the line is here. Then you can see something is happening here. The behavior is changed. Just thinking about that, and then thinking. And then later we're going to tell me. Okay. Okay, actually the answer is here. Okay, the point is, since we are in 40, you can see the line of stability was the Cn that were equal. But as I tell you, you look at 40, you can say before 40, nature preferred the number of protons and neutrons in the nucleus to be about the same. Yeah? After 40, they prefer when the neutrons are bigger to the proton. Because the nuclear force is independent of either the particular Nn and pair or pp. Then this thing actually is giving us information about how nature prefers to choose the correspondence between neutron and proton in the nucleus. We see that before 40, you kind of see that it follows the rule, like everybody is the same and trying to be balanced. After that point, you can say that it's becoming less stable, like you had more contribution and bigger than Earth. What this tells to us about the energy inside that, or what can happen? Because if the system is less stable, what can happen? It's gonna be having more trouble. Like you are gonna do something, the stability is gonna be lost quickly, for example. As the number of protons increase, the Coulomb force between all the protons becomes stronger until it's eventually affect the binding significantly. Then we see that this depends also on this quantity. Okay, and the work required to bind the charge inside the sphere is going to be infinity if this rule doesn't hold. Then if you come back and you look at the graphic, then you can say, okay, we can see that if we have higher number, we are going to have less stability in terms of the line. Okay, then for a singular proton, then we can have the variation of the column and the total repulsion that is going to depend of the relation that depends on the number of protons in the nucleus also. Yeah, and then we can do the analysis and look at the most stable nucleotides. Actually, if you look in the periodical table, you are going to find that they have even nucleotides, and the stables are going to have odd numbers. That is, for example, this one that are here. Then this line is showing to us how is the stability in the different case. Next time we're going to study the liquid drone model, but I would like to show you something nice. Here, okay, here. Okay, let me make it. Okay, I was telling to you about all the relation between bonding, non-bonding, and how is the structure. What happened is we had different components. For example, you had oxygen, carbon, and we had a big structure and chemicals, and we put everybody together. And we're trying to analyze what is happening with the force. Then, for example, you can see that you are going to have different kinds of materials. Some materials are strong. For example, if I begin to put this kind of hard, but if we had some plastic. When you had some plastic, you see that it's coming. It's having deformation, but you kind of stress and the distance is changed. Then something is the properties inside also are changed. Then I like you to show, for example, different case. I don't know if it's going to be so clear because the board is black. Probably I turn the light. Okay, this is actually something that we are doing with some carbon. Let's see. For example, I like you to see. Now you are pushing in the epsilon direction. You see how the atoms are kind of, something happening, stretching at maximum as they can, and then they break. Then it's some limit, like you had some limit and you had some external strength condition when this is going to happen. Oh, now is you push in the shield direction. Okay, now we are pulling in the other direction. See the form now is differently. than the other one, but it's gonna break in some point and then it's gonna also break in. Okay. And now, no, this. Okay, now I like to show you, for example, if we have some material that are permeable, then what happens? Sometimes they can let some particles to go and others not. Then they are gonna block some particles. Like for example, if the particles are bigger than the size of the hole, then it's not gonna enter. But then you can find some particles that can be the size and then can cruise. Then I like to show you this one. You see the small particles they are going? If the particles are too bigger, then they cannot enter. Now I'm gonna ask you something. How you can use this? What can you do with this thing? Like if you were in a company and somebody tell you, or whatever, what you can do with something like that? Because remember, this is a material that is only letting go small particles. It's not letting go big.
Letting go of strong particles or weak particles.
For example, can be if you like to differentiate some particles. For example, if you are trying to clean something because it has oil or has some, for example, petroleum in the water. Then you see what is the size of the oil, what is the size of the water, then you can use to clean, for example, because then it's going to only allow to pass some particles and others not. Or you can use to identify different components that are dangerous. Then it's going to say, oh, I'm going to let pass this material, and then I'm going to just put here, and the other are going to keep in the side. Then you are going to have classification. For example, if you are working with materials that are dangerous, then you kind of say, no, these guys don't pass, these guys can pass, then you kind of clean. It's like a filter, like the same thing that we use with the coffee, that doesn't let the coffee, the ground coffee go, but you have the water with the coffee and the flavor that is really good, but the coffee, the ground is not going. Then it can be used for that, but using in other things. And now I like to show you this one and also ask you the same question. Look this one. You see this yellow part? I just like you to think in what you can do with something like that. And you can observe what is happening also. Look what is happening. One time we're pushing and the other was compressed, and look what happened. Then the same question, what do you think that is happening there and what you can do with that?
Velcro.
Or you see it in the beginning, you see how it's changed, no? For example, the dimension. Here, this small surface is going with the upper part. And then you open, is you push, and you compress the other one. When you come back, this prefer to stay with the lower part. And the other one is not gonna take it. This can be used, for example, also to clean the surface. For example, is the yellowware oil again. Then you can have the system that if you put something, it's gonna kind of stay all the surface, the material surface that you like to clean or whatever, and then you are gonna just take it. But if you like to put this new thing in another material, to transport material, then you can do the opposite. Push one direction, compress the other direction, then the material is going down. Then you can use to transport something that you don't like to touch, or some chemicals or the oil, or depends where you were working. Yeah? Then this can be used for something like that. Okay, I think that I finished. I hope you liked it. You had any question? Okay. Then I see you Tuesday, I think so.
Wednesday.
Wednesday.
Wednesday, yes.